Section 6 is called the fundamental theorem of algebra. So yet another theorem. The nice thing is, the fundamental theorem is pretty simple. It's sitting right here. Every polynomial with a degree greater than 0. So that would be like degree 1 or 2 or 3 or so on. Okay? Every polynomial with a degree greater than 0 has at least one root in the set of complex numbers. And I think probably if you think about that, you already knew that. Right? Like even a first degree polynomial has a root. In the set of complex numbers though, that's a little bit different. Complex numbers look like this, a plus bi. If I have a real root, then the b, that number would be what? If I have a real root, then that means that there's no imaginary part, which means that the b would be, it's a number. Out of an infinite number of numbers.
Got it.
If I have a real root, then there is no imaginary part, which means the b would be 0. It has to be 0 in order for the imaginary part to disappear. So it turns out, you probably already knew this, or maybe you didn't think about it, so I'm going to point it out now. Real numbers are a subset of the complex numbers. Any real number can be written as a complex number. We talked about that before. Like the real number 4 can be written as 4 plus 0i. I don't know why I would ever want to do that, but I could do that. And that is why any real number is a part of the complex numbers. An imaginary root occurs when the graph doesn't cross the x-axis as many times as it should. Right?
Yes, sir.
Yes, we already know that, okay? So we actually already know this part of the fundamental theorem of algebra. The second part, a polynomial of degree n has exactly n roots in the set of complex numbers. That includes real roots. That includes double roots. And I think we already knew that too, right? Good. So for example, like basically what I've just told you is there's two parts to the fundamental theorem of algebra, and we already knew all of it. I've already taught it to you. So how many roots, real or not, does this polynomial right here have? 5. How many does this one have? 4. How many does this one have? 342. It's the degree of the leading coefficient, or the degree of the highest term. Huh? Yeah. It'll get harder. But that's the fundamental theorem of algebra right there. You already know it, which means you already know everything you need to know for this section.
Oh, no.
So what I want to do is summarize all the rules and theorems that you've learned in the last sections. You're going to use all of them in this section to help you find all of the roots of a polynomial. This section is a lot like the last section. So let's talk about the remainder theorem. What is the remainder theorem? No, but that's not what we used it for. We use synthetic division with the remainder theorem. Why?
Because I need to get it down to 0.
No.
When you have a remainder and just dividing regular numbers, you have to put like 0.0 and
No.
0.0 down.
Look it up. The remainder theorem is if I want to evaluate a polynomial at some number. So, I'm asked for f of a, and I want to evaluate the polynomial at that number. Then I can either take that number and substitute it into the polynomial, or I can use synthetic division. Like this, with an a right there. And then the remainder is the answer. So if I want to evaluate a polynomial at some number, that means I need to substitute that number into the polynomial. Or I can use synthetic division with that number right here. Do the synthetic division, and the remainder that I get is the same answer that I would have gotten had I done substitution. It's in your notes. What is the rational root theorem? What? It helps us find possible zeros. How?
Isn't that the one where we just do Q?
We do P equals the factors of what? Constant term. Q equals what? Factors of leading coefficient. So then, once we have P and Q, we go P over Q, and that gives us what? All of the possible rational roots. Doesn't list all of the roots possible, it just lists the possible rational roots. What's the conjugate root theorem? The conjugate root theorem says if you're given a root, a plus bi, so if a plus bi is a root, then what? A minus bi is a root also. That's why it's called the conjugate root theorem. Those two things are conjugates. This goes a little farther though, because also if a plus the square root of b is a root, then a minus the square root of b is also a root. Okay, we need to remember what Descartes' rule of signs is. The number of possible positive real roots, the number of possible positive or negative real roots, and the number of imaginary roots to balance out the total number of roots. Okay? So Descartes' rule of signs is it gives number of positive real roots from, how do we know how many positive real roots we can have? Yep. From the number of sign changes in the polynomial p of x. But it also gives the number of negative real roots from the number of sign changes in what? P of negative x. That's what Descartes' rule of signs does. And we use Descartes' rule of signs with the rational root theorem to narrow down the search for our real roots. And we just learned the fundamental theorem of algebra officially. It has two parts to it. The first one was what? fifth degree greater than 0 has at least one root, either real or imaginary. Also, the other part of the fundamental theorem of algebra is the degree of the polynomial is equal to the number of roots of the polynomial. So 2 parts to the fundamental theorem of algebra. These are all the theorems that we've learned so far. This one came from section 4, section 5, section 5, section 5, section 6. Here's a little flow chart for you to figure out how to find the zeros of your polynomial. In this section, you're going to be asked to find all the zeros of a polynomial. Here's how you do it. Start here. Question, can I use a calculator? Does it specifically say that I can't? If it specifically says no calculator, then your answer is no. If it doesn't say anything about a calculator, then your answer is yes, you can use a calculator. Now, let's assume for a second that we can't use a calculator. So, can I use a calculator? No. Then that means I need to use the rational root theorem. What is the rational root theorem? P over Q. Once I've done that, use Descartes' rule of signs. How do I use Descartes' rule of signs? Set up the table. Number positive, number negative, number imaginary, number total. Okay? Once you have that, then you can use the remainder theorem to determine your roots. In other words, use synthetic division. You set up your table for synthetic division. You're using the remainder theorem. We're using it all along. It's kind of like you had the power to go home all along. Same thing. This is the remainder theorem right here. Continue doing this until you have found enough to get your polynomial, your remaining polynomial, down to a second degree polynomial. That's what this one right here is telling you to do. Continue until the polynomial is factored down to a degree of 2. Once you've done that, use the quadratic formula, which we know is x equals negative b plus or minus square root b squared minus 4ac, all divided by 2a. Once you've done that, you're done. You have all your roots, no matter what degree you started with. If it does not specifically say that you can't use a calculator, then you can use a calculator. So, if you're going to use a calculator, then graph the polynomial on your calculator to find any real roots. Where will the real roots be that you find? On the x-axis. The zeros. X-intercepts. That's what you're looking for on your graph. Now, once you have those zeros from your graph, then you know the numbers that are going to work. You can avoid the rational root theorem. You can avoid using Descartes' rule of signs. You can avoid using the remainder theorem altogether. Well, no, I won't say that. But you can avoid these two for sure. Now, once you have those zeros, the real ones that actually are on your graph, then you're going to set up your synthetic division again and use those actual roots that you found. You know they're going to work. So you will quickly be able to get down to your second degree polynomial, hopefully. Once you're done doing that, do you have all the roots? If you have all the roots, then you're done. If you don't have all the roots, continue until the polynomial is factored down to a degree of 2. As you do this, you will probably get it down to a second degree polynomial. Once you get it down to a second degree polynomial, you don't have all the roots yet, but you can use the quadratic formula, and then you're done. So the question is, can you use your calculator or not? If you can, life becomes easy. If you can't, then you have to use all of these theorems. Example, what are all the roots of this polynomial? It specifically says no calculator. So that means we're going to have to follow the lower path on that flow chart. How many roots are we going to have here? 5. So how many roots do I have to find? Well, I have to have 5 answers. But how many do I have to find using all of my theorems? 3 of them. Get it down to a quadratic formula, or a quadratic, and then I can use the quadratic formula. Okay? So where do I need to start? P and Q. This is just like what we were doing in the last section. So P equals what?
Plus or minus 1, plus or minus 2, plus or minus 3.
Good. And Q equals?
Plus or minus 1.
Okay, so actually there's not a whole lot of options here, which is nice. P over Q equals? Those guys. Plus or minus 1, plus or minus 2, plus or minus 4. There's only 6 choices here. Now what?
Now we're going to set up our synthetic division.
No. We need Descartes' rule of signs to try to narrow this down. Maybe we can narrow it down to just 3 choices. We'll see. So, Descartes' rule of signs. Number of positive, number of negative, number of imaginary, number total. How do we get the number of positive possible roots?
You have the number of signs.
How many sign changes do we have in our polynomial?
Yeah, 4.
There's 4.
Yeah.
We start positive, switch to negative, that's 1. Stay negative, switch to positive, that's 2. Switch to negative, that's 3. Switch back to positive, that's 4. Okay? F of negative x equals. Good? 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 Okay, good. How many sign changes do we have? 1. How many roots total should I have?
5.
How many do I have written down here?
5.
So how many imaginary in this case?
0.
Okay. Okay, now what do we do from here? Yeah, the positives do come down by an even number each time. Will I be able to change any of the negative roots? No. Okay, so I'm going to hold that constant, and then I could have how many positives? 2, which gives me how many imaginary? 2 for a total of 5. I can still decrease the positives, so I'll leave that at 1 there, and then I have how many positives here? 0. 4 imaginaries, 5 here. And that's it. There's only 3 ways that this can occur. Now, what numbers am I going to try to pick? I'm guaranteed in all 3 of these cases a negative real root. So I'm going to go with negative numbers. Now we can set up our synthetic division. What goes across the top?
1, negative 1, negative 3, negative 4, 4.
Good. This is the rational, or not the rational root theorem. This is the remainder theorem that we're using here. If we get a remainder of 0, then that means that the value of the function at that x coordinate is 0, which means that we have an x-intercept, which means we have a root, which means we have a 0. Okay? They're all connected. So, give me a number to pick.
Start with negative 1.
Sure, try negative 1. So the 1 comes down. Negative 1 plus negative 1 is negative 2. That gives me 2 plus negative 3 is negative 1. Multiply and I get 1 plus 3 is 4.
Negative 4 would be
Negative
negative 8.
8.
No, 4.
So I get what here?
Positive.
Positive 12. So that one didn't work. So try another one. What? Okay, there's 5 real roots, or there's 5 roots, right? But I don't know if it's this line, or this line, or this line. I'm only checking the negative roots right now. I'm trying to get this guy right here. If I get this guy, I might be able to get a positive one after that. But I'm not going to start until I get that negative one. Okay? So negative 1 didn't work. What should we try now? All right, try negative 2. The 1 still comes down. We have negative 2 plus negative 1, so negative 3. And then, yep, we get 3 here. And then negative 3 here. And then positive 2 and 0. So negative 2 did work, which means that x equals negative 2 is a solution. It's a root. And now we're down to what degree polynomial? A 4th degree polynomial. And because of Descartes' rule of signs, am I gonna check negative 4? Nope, because I found the only negative real root that is possible. Okay? So now we're going to check the positives. So try 1. We're using this line here now. So this one comes down. And what do we get? Negative 2. It's 1 times 1 plus negative 3, negative 2. Negative 2 times 1 is negative 2 plus 3 is 1. 1 times 1 is 1 plus negative 3 is negative 2 times 1 is negative 2 plus 2 is 0. So 1 works. X equals 1 is a root. Now, because of Descartes' rule of signs, I just found a positive real root. Can I find another? Yes, because I'm either on this line or I'm on this line. Not this one. So now I can find another, and then once I do, what degree am I at right now? Once I find that next one, what degree will I be at? 2, and then I'll be able to use the quadratic formula. So, draw a line, find another root. What do you want to pick? 2, positive 2, okay. So the 1 comes down. 2 times 1 is 2, plus negative 2 is 0. So I have 0 plus 1, which is 1. 2 times 1 is 2, plus negative 2 is 0, which means positive 2 also works. So x equals positive 2 is a root. Now I have 3 of them. Now what? This is x squared plus 1 equals 0. Now what? Solve for x. In this case, I don't have to factor it. I can move the 1 over and then use the square root property. So I have x squared equals negative 1. Square root both sides, and I get x equals what? That is plus or minus I. So x equals plus or minus I are your last 2 roots. You got all 5. 3 of them were real, 2 of them were imaginary. For this problem, what are all the roots of this polynomial? And this time I'm specifically telling you that you can use a calculator. I might not specifically tell you that you can't, which means I might not specifically say that you can. If it specifically says you can't, then you can't. But if it doesn't say anything, then you can. And if you can, then you should. Because it's going to save you a lot of time. So, on our calculators, we're going to enter in that polynomial on the graph. And that polynomial is hidden, so let me find it. Okay, we have x to the 4th. Make sure you're getting out of your exponent each time. Plus x to the 3rd. Minus 7x squared. Minus 9x. Minus 18. Hit enter. How many roots should I have in this polynomial? 4. How many do I see on my graph right now? 2. How many do I have to find so that then I can use the quadratic formula? And I have 2 sitting right here. So all I need to do is have the calculator calculate those roots for me. So analyze graph, 0. Lower bound, upper bound, got an ordered pair. I have negative 3 is a root. Menu, analyze graph, 0, lower bound, upper bound. and positive 3 is a 0. As soon as I have that, then I know that x equals 3, x equals negative 3 are both solutions to my polynomial. I don't have to do p, q, p over q. I don't have to do Descartes' rule of signs. I already know 2 of my roots. So now what's going to happen is set up your remainder theorem, set up the synthetic division, write the coefficients of the polynomial across the top. So it's 1, 1, negative 7, negative 9, negative 18. And then put these numbers directly in, because we know their roots. So we know that we'll get a remainder of 0 over here. I plug 3 in here, the 1 comes down. 3 times 1 is 3, plus 1 is 4. 4 times 3 is 12, plus negative 7 is 5. 5 times 3 is 15, plus negative 9 is 6. 6 times 3 is 18, plus negative 18 is 0. So of course 3 worked. We already knew that it did. Now try negative 3. We know it's going to work as well. I can use this remaining polynomial. The 1 comes down. 1 times negative 3 is negative 3 plus 4 is 1. We get negative 3 plus 5 is 2. 2 times negative 3 is negative 6 plus 6 is 0. And of course negative 3 worked. We knew it was going to. Now I'm down to a second degree polynomial sitting here. X squared plus x plus 2 equals 0. If it factors, it's going to be two numbers that multiply to give me 2, but add to give me 1. Not going to work here, so it's going to be quadratic formula for sure. X equals negative 1 plus or minus square root 1 minus 4 times 1 times 2, all divided by 2. X equals negative 1 plus or minus square root 1 minus 8 is negative 7 over 2. So this becomes x equals negative 1 plus or minus I root 7 over 2. There are your other two roots. So we have all 4.